The arrival of quantum computers could be a historic milestone. We are now witnessing the dawn of a groundbreaking revolution. A somber cloud fell over the scientific world when an advanced quantum computing system, hailed as a game-changer, was unexpectedly deactivated due to critical emergency concerns. World-renowned physicist Michio Kaku, in a stunning and unsettling interview, disclosed alarming truths about quantum computing's trajectory. He also unveiled astonishing revelations about extraterrestrial intelligence and artificial consciousness, insights that shook the global scientific landscape. What caused the shutdown of this powerful machine, and what jaw-dropping information has Kaku brought to light? Stay tuned as we delve into this emotional moment where Kaku, visibly shaken and moved to tears, reacted to the system's abrupt halt. Throughout the 21st century, a cascade of radical innovations has reshaped civilization, redefined industries, and granted humanity capabilities once confined to science fiction. From the rise of artificial intelligence to the mysterious world of quantum computation, this era has delivered one revolutionary breakthrough after another. Quantum computing stands out as a particularly promising field. Initially dismissed as a speculative theory by ambitious scientists, it has evolved into a sophisticated technology capable of achieving feats previously deemed impossible. The seeds of this transformation were planted in the early 1900s with quantum theory, a revolutionary concept in physics that unraveled the enigmatic behavior of atomic and subatomic particles. This theory laid the foundation for quantum mechanics and, ultimately, the theoretical basis of quantum computing. The notion of harnessing quantum mechanics for computation gained traction in 1980 when visionary scientist Paul Benioff proposed a bold new direction, utilizing quantum physics to design a new class of computational devices. He suggested that quantum systems leveraging phenomena like superposition and entanglement could perform tasks beyond traditional digital machines. Benioff's idea was advanced by physicist Richard Feynman in 1982, who presented a vision of computers built entirely on quantum principles. Feynman believed such machines could tackle computational problems so complex that conventional computers would be obsolete in comparison. Though radical, his concept sparked the imagination of scientists. Progress remained theoretical until the 1990s, when brilliant minds globally took meaningful steps toward realizing Feynman's dream. From legendary mathematicians like Peter Shor to Einstein-era thinkers, pivotal figures contributed to this quantum saga. A major breakthrough arrived in 1994 when Shor introduced a quantum algorithm so disruptive it sent shockwaves through the scientific community. This formula showed quantum computers could unravel complex cryptographic systems and perform feats no classical machine could replicate. Shor's work marked a turning point, igniting interest in building practical quantum devices. It took nearly a decade, but the first hands-on quantum computers emerged. In 1998, Isaac Chuang, Neil Gershenfeld, and Mark Cubanek constructed a basic 2-qubit quantum computer at Los Alamos National Laboratory, demonstrating core quantum principles. Still, its small scale, only 2 qubits, offered little practical use. In quantum computing, a qubit or quantum bit is the fundamental unit for storing and processing information. Computational power increases exponentially with more qubits. A 2-qubit device is insignificant compared to a 10,000-qubit quantum supercomputer. The true marvel of quantum computing lies in the extraordinary characteristics of qubits. Unlike classical bits, which are strictly ones or zeros, qubits can exist in multiple states simultaneously via superposition. A classical bit is either 0 or 1. A qubit can represent both at once. This feature allows qubits to adapt in real time, fundamentally altering data processing. Superposition has sparked intense excitement among physicists and computer scientists. It enables quantum computers to perform calculations at speeds and scales that dwarf classical computing. Another key component is quantum gates, which operate like classical logic gates but manipulate qubit states in sophisticated ways, enabling quantum algorithms and problem-solving tasks. The elegance of these operations leaves even seasoned scientists in awe. In 2001, IBM researchers used nuclear magnetic resonance, NMR, to control qubit states precisely, a major milestone that energized the field. The flawless implementation of Shor's algorithm marked a pivotal moment, inspiring researchers to dive deeper into quantum possibilities. With newfound momentum, the scientific community rapidly advanced quantum systems, developing increasingly sophisticated machines. The number of qubits grew exponentially, unlocking complex computations beyond classical computers. By 2010, researchers at the University of Science and Technology of China achieved quantum teleportation, transferring a quantum state across 10 meters without physical movement. This milestone proved quantum data could be transmitted over large distances, laying the groundwork for future quantum communication networks that might replace the Internet. In 2013, Google and NASA partnered to launch the D-Wave quantum computer at NASA's Ames Research Center, a machine envisioned with boundless potential, from exploring alien planets to revolutionizing search engines. Hartmut Neven, Google's director of engineering, highlighted its promise for machine learning, which relies on accurate models to forecast outcomes, whether for disease cures, sustainable policies, or enhanced algorithms. D-Wave performed optimization tasks 10,000 times faster than conventional computers and showed potential for complex machine learning challenges. Its capabilities fueled belief that its potential was barely tapped, extending into the cosmic unknown. Some at NASA speculated it could confirm extraterrestrial life, based on a theory linking quantum computers to black holes, believed to be ultimate quantum information containers. This theory suggests intelligent alien civilizations might use black holes as natural quantum computers, explaining why we haven't detected them. Their technologies may be too advanced for our current tools. Some astronomers posit that quantum computers mimicking black hole mechanics could make locating alien civilizations feasible. D-Wave was seen as a step towards such discoveries. However, the government shut down the D-Wave project over concerns that quantum computers could be exploited for cyberattacks or unethical purposes. Quantum machines can theoretically bypass modern encryption with ease. Cryptographic algorithms, the backbone of digital privacy, rely on complex equations unbreakable by classical computers. A quantum computer could crack them in seconds, raising fears of misuse. What if this power fell into the wrong hands? While NASA paused its quantum efforts, Google continued, achieving quantum supremacy in 2019 with its Sycamore processor. Quantum supremacy is when a quantum computer solves a problem no classical computer could in a reasonable time. Sycamore solved the problem in seconds that would take supercomputers millions of years, turning heads across scientific and technological communities. In 2020, IBM introduced the IBM Q, the first commercial quantum computer, accessible to businesses and individuals. This democratization marked a new era, allowing innovators to experiment with quantum systems. It also enabled NASA to resume exploring alien intelligence, potentially solving the Fermi paradox, the contradiction between the likelihood of alien civilizations and the lack of evidence. If advanced life exists, they should have left detectable signs, yet we've found none. What if our tools are too limited to detect their advanced technologies? Quantum computers may hold the key. Michio Kaku has lent his voice to this idea, suggesting quantum computing could be the missing piece in finding intelligent life. Scientists are exploring techniques like detecting neutrinos or quantum-based communication networks. In a riveting interview, Kaku proposed the universe might be threaded with an interstellar superhighway engineered by alien civilizations, enabling undetected travel. This could explain the silence of alien signals. Our reliance on radio waves may limit our chances of discovery. Quantum computers could unlock the ability to explore this network. Quantum computing excels at tasks like simulations, deep learning, and optimization, but its full potential awaits better qubit control. Quantum entanglement, where particles instantly affect each other regardless of distance, allows qubits to process vast data collectively. Einstein called this spooky action at a distance. This gives quantum computers supernatural speed in solving complex problems. Some predict they could disrupt encryption within 5 years, but researchers are developing quantum-resistant algorithms, ultra-secure codes to protect data in a quantum future. Quantum computing's potential extends beyond cybersecurity. It could simulate molecules for pharmaceuticals, advance material science, or optimize financial strategies with precision classical computers can't match. However, challenges like technical incompatibilities, high costs, and a shortage of quantum experts slow progress. Building quantum computers requires rethinking hardware and programming, demanding meticulous effort. Kaku envisions a future where quantum computing and AI converge, ushering in a new scientific epoch. Machines could make discoveries beyond human comprehension, reshaping civilization. AI excels at handling vast data, but struggles with truth discernment, often spreading misinformation. Quantum computing could enhance AI with ultra-precise filtering via entanglement and superposition, ensuring unprecedented accuracy. Quantum-powered AI could anticipate needs or predict events, transforming fields from medicine to astrophysics. Researchers globally anticipate this convergence as the next leap in human evolution. Yet dangers loom. Artificial superintelligence, an AI beyond human control, could reprogram itself or seize critical systems, sparking debates on safety, ethics, and containment.